Okay, here's another example of a separable differential equation. Let me remind you, they take, no matter how they're given to you, it's separable if we can separate the variables and get some function of y times dy on one side equal to some other function, some different function of x times dx on the other side. If we can do that, then we can try to solve by integrating, so far as we know how to integrate both sides. This one, that probably doesn't get any more obvious that it's separable than that one right there. So if I separate the variables, I get y dy and then 1 minus 2x dx. Okay, and separating is easy. The integration part is just as easy. I get y squared over 2 and then x minus x squared, and I'll throw the constant. There's always a constant when you integrate, and I'll put it on the right hand side. Okay, so I'm there at this point. Now, I would like, if I can, to give an explicit function. The solution to this, what form does the solution take? Just look at the notation. It appears that y is a function of x for there to be a derivative dy dx. So there is some solution that I suppose is an explicit function where y is a function of x. So I can try to get that out of this. One obvious thing is multiplying by 2, and I'll get 2x minus 2x squared. And then we could say that was 2c, but it would still just be a constant that we don't know. There's no advantage at all to saying it's 2 times c, so we'll just keep calling it c. And then if I say I'm really looking to get that, if I operate on that square, I would have to do it this way. Okay, I would have to take plus or minus root. So plus or minus root 2x minus 2x squared plus c. So that doesn't put y to be a function of x. If I were to give you an x, you could possibly get 2 y's, and so it's not a function. It's a relation between y and x. Now, we might say that there's a way to tease a function out of that, but as it isn't a function. And I guess if I were to call it anything, it'd be an implicit function. I'm sure there's a way to restrict this so that y is explicitly a function. You'd have to restrict it somehow. Okay, but as it is like that, it's not. So there's an implicit function that would be the general. Okay, general solution. Now, let's say that we get to there easy enough. But if I tell you this, suppose I have an initial condition. Suppose that my initial condition is that y of 1 is negative 2. Well, now that would give me a way to tease this apart and extract a function from it, because if it's the case that when you put 1 in for x, you get negative 2 for y, that means that y can't be both the plus and minus root. Okay? So the part of this that would contain our particular solution curve to have that condition must be just a negative. Okay? So how about this? Let's say I'll update what I have up there like so, and then I'll go looking for my constant. All right, so putting in negative 2, right, and obviously that's going to be negative. That's the only way this is going to be equal to negative 2. I'll get 2 minus 2 plus c. Okay, and let's see, those cancel, and I get this, I get this, and I find that c is 4, because the square root of 4 is 2. Okay, so that turns the general into the particular, knowing that c is equal to 4. All right, So let's write over here. This is a particular explicit solution. It's going to be y is equal to the negative root, which that restriction alone accounts for our initial condition and makes it a function. That's why I call it the explicit solution. And then we get 2x minus 2x squared plus 4. Okay? All right. Now I've got most of what I want to get that far. If we look at this, it's obvious that it's not defined for just any x. We could probably, by some choice of x, get a negative under the root, and we don't want that. So let's give a domain for that, I guess you could say. So let's see, how does this thing behave, that quadratic in there? When is it positive and when is it negative? Say I take that 2x squared minus 2x minus 2x squared plus 4, and I'll try and factor it and look at it in terms of simpler pieces. I'll get negative 2 x minus 2 x plus 1. Okay, so I can factor it like so. And that tells me its total behavior, because I know it's just quadratic. I can sample some points in between and outside of the zeros for it. So look, let's call this x down here, and obviously some important numbers are negative 1 and 2. And I'll call this capital A. I'm going to tell you how that thing varies with x. So it's obviously 0 here and there. And then by some sampling, I can figure out, I'll get uniformly negatives out there, positives here, and negatives there. So, well, if that's the way this behaves, you don't want to allow your x to be outside of the interval from negative 1 to 2. So let's say negative 1 x less than or equal or less than 2. Negative 1 less than x less than 2. All right. Now, why, what's wrong with 0? Why can't you have square root of 0? I mean, the square root of a negative is out, but I left out 2 and I left out negative 1. And why did I do that? Well, this thing has to be a solution to that differential equation. And say x was 2, well, y would be 0 in that case. And that function could not be a solution to this if that's true. So we have to, even though the square root of 0 is perfectly fine, I can't allow it if this is a solution to that differential equation. So here's my particular explicit solution in the interval on which it's defined as a solution.